Right. Okay, I think things are stabilizing a little bit now in terms of numbers on this meeting. Good afternoon, and welcome to the first of hopefully many UK Hydrogels Network's seminars online. Just a little bit of housekeeping here. It's going to be, even though this talk today might be a little bit fluid mechanics, applied maths based, our hope with these seminars is that we bring people together from lots of different disciplines who are interested in hydrogels. That includes applied maths, that includes chemistry, that includes polymer physics, lots of different fields. If you've got any questions about any of these, or you're interested in taking part in the future, contact me, Matt Butler, or Matt Hennessy. The three of us are running these things. And today we're going to be hearing from Danny Booth, who normally sits about 2 meters to the right of where I'm sat now. He's a postdoc in Tom Montenegro Johnson's group here at the University of Warwick. He did his PhD with Ian Griffiths and Peter Howell, got that right, yes, at Oxford, finished at the beginning of the middle of last year, and has been at Warwick now for a few months. So I might well hand over to Danny, and we look forward to hearing what you've been working on.
Yeah, well, thanks for that, Joe. Yeah, so as Joe said, this is stuff that I've been working on for the past few months. So some of this, at least at the beginning, is stuff that I've done very recently, with some of the hydrogel stuff being stuff that I got working yesterday. So it'd be great to hear people's opinions on some of the stuff that I've been doing. So my talk's going to be on controllable microfluidics through active droplets and responsive hydrogels. So that's just a couple of buzzwords right there. So let's just have a look at what they mean. So we're in a hydrogels talk, so start off with the responsive hydrogels part. So hydrogels are these hydrophilic polymer matrices that get surrounded by lots of water. So the canonical example of this is the kids' toy Orbeez, these small beads that expand to many times their size by absorbing in water. And responsive hydrogels have these chemical properties that if you, for example, heat them up, they lose their affinity for water and then expel that water, so then they shrink. And we want to be able to see how we can use that alongside active droplets. So active droplets is also something that's been studied quite a lot recently with because they've been shown that they can self-propel. So this is where you have a droplet of water in a surfactant-laden oil, for example, and these droplets will self-propel themselves around by having these solubilizing reactions. So we look at these as they have a surface reaction, which then through an interaction layer generates a phoretic slip. So it just adds a slip velocity around the droplet, and that slip velocity then drives fluid flow. So like I said, we wanted to combine these two ideas, and our idea is for a microfluidic device where you make the walls of the device out of this responsive hydrogel. And then when you stimulate it at a specific point, you generate a droplet of an active fluid droplet along the surface of your microfluidic device. And then the phoretic slip then generates fluid flows inside the device itself. So the advantages of this is that you can get fluid flow without having to supply an external pressure drop across your device. So this is going to be the bit that I got working yesterday. So I'm going to first split it into two. I'm going to split it into two parts. I'm first going to look at the hydrogel modeling aspect, and then in the second half, I'll look at this device and what sort of flows we can get. So to simplify things for the hydrogels part, we're just going to look at a uniaxial deformation. So that just means that it's constrained in 2 spatial dimensions and can only shrink or expand in 1 spatial dimension. So you can go through all the hydrogel maths by starting with your free energy and have a neo-Hookean for your elastic energy and a Florey-Huggins for your mixing, but that's all been done before. But essentially, going through all of that, you just get this one relatively simple PDE, which is just a advection diffusion style equation, but it's non-linear, so it's a bit messier, but essentially is something that's just an equation for your porosity. And then we have it, so initially we have this fully swollen state, we heat it up, it then wants to shrink, and then that expels water, and then it's that expulsion of water that creates the droplet. So our boundary conditions are just fully initially swollen, and then at the top and bottom boundaries, we have a force balance. And so because this is going into a different fluid at the top, so like we're saying it's like into an surfactant-laden oil, you could imagine that you have different pressure drops across the top and bottom of your hydrogel here. But for now, I'm just assuming that that pressure drop is the same across both ends. And all this means is that if you assume that, then your porosity is the same at both endpoints. And then we can work out what these porosity would be by working out this force balance. So this is just then the balance of your elastic stress with your osmotic component. And then this term here then just takes into account your the affinity for the mixing and how it depends on temperature and your porosity itself. So these just take some numerical values that are taken from some data sets that Matt Butler and Tom did in their 2022 paper. And then you can get this curve for finding out what your equilibrium porosity will be as a function of the temperature you're heating it at. So for example, if you look at the A and B data set here, if you're initially at 300 Kelvin, then your porosity is about 0.6. And then if you heat it up to say 310, you're closer to 0.2. So you go from a high porosity to then shrinking and being a low porosity. So then again, just going back to then our equations, is then it's just re-saying what we did before, except now instead of saying, oh, we have this force balance at our endpoints, you just say that actually it's just this fixed porosity. And with what I said before, if you had a different pressure drop across your hydrogel, this boundary condition on x naught and x equals naught and x equals a of t, you would just have different values each side. And then that could just give you a different flux through. So this is all well and good, just some maths, but like, what does this actually give us? So this is, so like what I was saying is we heat from a hydrogel initially at 300 Kelvin to 310. We see that we have a shrinking hydrogel, which is what we were expecting. And then this gives us some flux out. And this is a bit wiggly right now, but this is because, as you can see, if you're looking at the porosity as a function of position along the hydrogel, is you get this sharp front appearing. And I think that these are just a numerical artifact right now of this sharp front moving. And if anyone has any suggestions of how to make this a bit better, it would be helpful, but this is all I have right now. And so then what we can do is then take this flux out and link this up with a droplet forming equation. So if we just look at 2D, then you have, and if you assume you're smaller than the capillary length, your droplet is just going to be a circular cap or in 3D, it would be a spherical cap. And you can then just write down an equation for your volume or area of your drop, and then that's going to increase with respect to your flux going in, and you can then just write down this equation. You get something similar if you look at 3D, and your contact angle is then just increasing, and you get a droplet that rises. And then the nice thing about hydrogels is that we can go from having it heated at 310 Kelvin to then cooling it back down to 300 Kelvin and just do what we did, but in reverse. And we see that our hydrogel goes from half its length to back to its full length. And you also get a flux back, and then that flux will reabsorb that droplet that was formed. So this gives you a deployable mechanism for where you have your droplets in the device. So this again here, so this is like, so you have it activated, you form this droplet on the surface, you take away the activation, and it will suck it back in. So that's all the hydrogel stuff. Now, how does this relate to the microfluidic device itself? So what we say is that we have some surfactant-laden oil inside the device. So that's governed by an advection diffusion equation. And then we have Stokes flow for the fluid flow. And then we have a theoretic slip velocity along the droplet itself, which is given by this. U is your tangential gradient of your concentration. So how does this all actually look? So these are just some solution profiles if we had the Peclet number being 0, so everything's diffusion dominated, but you can get similar things if you have finite Peclet number. So what you get is you get larger concentration around where your droplet is. So in this case, in A, it's just between 4 and 6. So you have higher concentration here. This drives a slip velocity, which then creates these circulating flows. And then you can do the same by having more droplets, and you just get different places where you have these circulating flows. So circulating flows by themselves, it doesn't really give us anything because we want to be able to pump fluid or to transport things around the device. But this is where the deployable nature of these active droplets comes in, because we can activate different regions of the responsive hydrogel to form droplets in different regions of the device. So we can use this, in fact, to be able to do particle transport. So we initially here have a particle, and then we have just the droplet between 2 and 3, and then we swap it between 4 and 6. And then again, we swap it to then being between 6 and 8. And you see we can get this sequential dragging of the particle along the device. And so if we only use one droplet, we tend to get this, the particle being directed towards the walls of the device. Whereas if we have 2 droplets, one on the top and one on the bottom, like in this case, we can get the particle being directed towards the center of the channel instead. So you could think of this as you could remove unwanted reagents to the outsides of the channel because you don't want them in your system, or you can use like this system to drag reagents towards the center as so then some extraction point. This gives us some targeted way of transporting particles. And as you can see, that actually is the last step is quite slow. there actually is a strong dependence on how long between each of these steps that you change where your droplet position is to get an optimal travel time. So you can actually then calculate what these optimal travel times are, or what you can also do is supply active control. So you move the stimulus of where the droplet is along at the same speed as the particle is going to then effectively have the droplet dragging the particle along, and you'll get even faster times than these by just having them in discrete places. So another important aspect that is useful in microfluidic devices is to be able to have chaotic mixing. So in Stokes flow, everything's laminar, and mixing then tends to happen on diffusive timescales, which can take ages. So how we can get chaotic mixing in our system is to have these two setups and flip between them with a set time interval between. So we initially have the first one on for t seconds, and then we swap over to the second configuration for t seconds, and then you swap over, and you keep just flitting between these two systems. And you can see that if you do different time steps here, if you just do an initially small time step, you still have these quite large void regions where the particles never go. Whereas if you increase the time step between them, you explore more and more of the device space. And then finally, if you do t equals 6, you pretty much explore everywhere, and your solution is then well mixed. These all again. So yeah, so just a quick summary about what we've gone over. So yeah, I've developed a model for this uniaxial deformation of the hydrogel, which then allows us to form a droplet. And then we've utilized these droplets to drive a fluid flow without having the need of an external pressure drop. And they can be used to transport particles, and they can be used for chaotic mixing. So now I've just got a couple of other things as more just work that I've started, but it's not fully gotten anywhere yet. So I've said all this stuff about without needing the use of an external pressure drop across the system, but how can we also use these in conjunction with a pressure drop across? So one idea that we've had is this particle trap. So if you have a channel with a little notch in it and you apply a pressure drop across, you'll get a Poisson flow going through. And so if you look at the droplet off case, yes, this is just Poisson flow going through. And then in the little notched out region, you just get these circulating flows going around because it's being forced by the Poisson flow beneath it. Whereas then if you have an active droplet along one of the walls of that notch, you can then use that to drag the streamlines into that region. So that could transport particles into that region and then turn off the droplet. And then that traps particles within this notch. So then you can have this as like a reaction site or something along those lines. So it's just a way to be able to collect particles in a specific region of your device. And then another thing that we've been working on is using these in a branching channel system. So instead of just having a notch, you have your channel and then it splits off into two. And then using these active droplets, you can then control how much fluid goes through each branch of the channel. So we can see in the graph on the right, this is the flux through the top branch. And we see that if we increase the strength of the droplet in comparison to the pressure drop, we actually can get quite a lot more fluid flow going up the top branch than the bottom branch, because if the droplet wasn't turned on at all, you'd just expect 50-50 split between the two branches. And I think that's it. So thanks everyone for listening, and I'd really appreciate if you have any questions for me, or yeah.
And thank you, Danny. And just to say, you're more than welcome to unmute yourself to ask a question. But if you'd rather not be recorded, I will keep an eye on the chat and I can read out any questions that appear on there. So yeah, I'll just give people a couple of seconds if anyone wants to come forward with a question.
Yeah, I've got a couple of questions, Danny, for you.
Yeah.
So the first question is, these are more about realizing this in an experiment, I suppose. So if you have this like hydrogel, which is surrounded by a surfactant containing solution, is there any potential for the surfactant to actually diffuse into the gel and then completely like mess up the thermal responsiveness of it?
I think that could definitely be an issue that you would have with it. But yeah, I don't know so much about how surfactants go into a hydrogel, or like, because it could get stuck into the polymer matrix itself, or yeah, I'm not 100% sure on how that would work.
Mm-hmm. And then in terms of the heating as well, how do you envision like heating these gels locally?
Yeah, well, so I guess there's also other methods that you could use instead of just heating, so that you can have like pH responsive gels or light responsive gels, which may be easier to have in like a microfluidic system. Yeah, it's just that I know a lot of work has been done so far in thermoresponsive, and yeah, like I said, I literally got this work. I got the hydrogel stuff working yesterday. So.
Awesome, cool, thanks.
I think there's a raised hand, so if you'd like to unmute yourself and ask your question, go ahead.
Yeah, thank you so much. I am Egypt too. So I just want to ask a question regarding you mentioned that you've not applied external pressure, but in your constitutive equation I can see a pressure gradient. Can you explain more about that?
In which part? In the device part or the hydrogel bit?
Yeah, so if you go back to your constitutive equation, that's I think
Is it this?
Yeah, here. So you can see that there's a pressure gradient here in the second equation. So and you were mentioning something that you didn't apply any external pressure. So can you?
So that's just your fluid pressure. So we've not. So by a external pressure drop, I mean, so like generally, what would be done in like these devices is you supply like zero pressure here, and then a negative pressure over here, and that would drive your fluid flow across. Whereas in our system, the pressure here, pressure at the endpoints is the same. So there's no pressure. So it's not like, so usually like you inject at one end and you suck out at the other end. Is we don't have that system.
Yeah, exactly.
Closed.
Yeah, I get it, because I'm modeling the same system. I actually understand now.
Yeah. So
yeah. Thank you.
Otherwise.
And Pratik has a raised hand as well.
Hello. So I'm Pratik. So I just wanted to know regarding the transport phenomena. Whatever is happening in the channel made up of hydrogels. So is there any? I just wanted to know whatever the constitutive relation has been used regarding the modeling part of the hydrogels particularly. Thank you.
So so modeling the hydrogels part, I skipped over that a bit. But yeah, so this is just so you can derive these from just like the neo-Hookean elasticity and a Flory-Huggins model for the mixing between the two, and then you use that. You've got Darcy velocity. Yeah, your fluid flow is driven by Darcy flow inside the polymer matrix itself, and you can just you can work through a page or two of algebra. And
so whatever the equations can be used in for the flow through porous media, the same equations can be used over here as well.
So it's Darcy flow, which is what you use for porous media.
Okay.
Yeah.
Okay. And the phi, whatever has been used over here, that is the volume fraction. Am I correct?
That's it's the porosity. The fluid volume fraction.
So the fluid volume fraction. So what the fluid is all about here, is it the fluid of the surfactant fluid is the surfactant laden oil droplet or something else?
So this will just be water. So the system is so you essentially have water inside your hydrogels, and then a surfactant laden oil inside the device in this part. So you have water inside here, which then gets driven out when you apply a response to the hydrogel.
Okay, and one more quick question I have. So how do you track the position of the surfactant laden droplet? Since you are saying these are active droplets, so I can understand. So they will be self-propelling, but my question was on understanding the trajectory of the droplet. So if you can elaborate, then that would be.
Yeah. So in this system, we're not using the fact that they're self-propelling. We generate the droplet and have it pinned at the surface of the device.
Okay.
So then, and then with it being pinned there, it's then driving these circulatory flows around. Whereas if you had like a fully spherical droplet, then yes, you can get it then self-propelling. But we're keeping it pinned at the wall.
Okay, so basically the droplets are getting pinned at the hydrogel interface, hydrogel and liquid interface.
Yeah.
Okay. So then how the droplets are moving? So then there should be some external force applied within the channel itself.
So the droplet is moving by applying a stimulus at different places along the hydrogel. So it's not the same droplet moving along. It's you apply the stimulus at one point, that forms a droplet there. Then you release that stimulus, the droplet is absorbed back. You apply a stimulus somewhere else, and that forms a new droplet.
Okay, now I understand. So the stimuli, whatever has been applied over here, that's basically intrinsic to the hydrogel itself. So the hydrogel is basically doing the action. It's basically the normal action kind of thing. So if I do Young's equation over there, so basically in Young's equation, the tangential force and the normal force gets balanced. So the normal force in this case is basically substantial enough so that I get that droplet bumping over there, right?
Yes.
Okay.
Yes.
Okay. Thank you very much for clarifying my doubts. Thank you.
That's okay.
Thank you. I think also Tom in the chat clarified some of those doubts as well. I think there's one more raised hand and from Yashpal, and I reckon he's got a question as well. I don't know whether we can't hear you, but I don't know whether that's a problem on my end or on yours.
I can't hear.
Okay. Well.
Can you hear me? Can you hear me now?
Yeah, I can hear you
there
now.
we go. Yes,
Yeah.
that works. Yeah.
Okay. It was a problem on my end, sorry. My question was regarding flux of water as well. When the fluxes are small, it is you're considering that the water droplet is thin, but will it also deform, or are the fluxes strong enough to deform the consecutive water droplet that you are creating? You get my point?
So that is also something that we're working on as well. Is like if we could make these fluxes large enough that you can then form a fully droplet that then pinches off, and then it's a way to then create these active droplets.
My point was not to create active droplets. My question was that if whether or not the fluxes are strong enough to cause deformations within the, let us say, the small bump that you're creating. So you create a small bump at one point,
yes.
The particles move forward, then you create a bump at the second point, right?
Yes.
So at the second point, do the fluxes deform the bump or droplet, if you want to call it, the droplet? Is it still spherical, or is it, let us say, moved towards the flow? It's slightly deformed or a bit more elastic, is my question.
I do not. I would assume with these with the thinking that these are in microfluidic devices, so everything's really small, your surface tension is going to be sufficiently high that they're going to pretty much be spherical. But yeah, I'm not 100% sure, to be perfectly honest.
I think Tom might be, by the looks of the chat. Or it sounds like he's 100% sure.
Yeah.
You can see that he's typing.
The trick is to always sound like you're 100% sure, Joe.
Yeah.
No, it's what Danny said, really. Essentially, if you look at self-propelling active droplets, they more or less always remain spherical.
Yeah.
Even when active droplets get very, very close to one another.
Yeah.
Because they're on such small scales. In this case, the little bump isn't actually a bump in the hydrogel itself, but the droplet. So once the stimulus is taken away, that region of the hydrogel actually sucks that bump back in.
Yeah.
A bit like me sucking in my stomach every time I have to go swimming. So once the next one's formed, you're sort of turning that one off. But in the chaotic mixing case, you do have multiple at the same time. I would say that the deformation of the surface is far more likely to come from self-interaction, because the slip flows that each one is producing are going to be far greater than the lower order interaction flows. And even then, it's probably not going to be enough to stop it being spherical.
No, I don't think so.
Essentially, the symmetry of the shape will be maintained in that scenario, I suppose, right?
Yeah. Yeah, the symmetry of the shape will be, because of the such high surface tension, it will be a spherical cap.
Thank you.
Yeah. Thanks.
Excellent. And Matt Hennessy again. Yep. So.
Yeah, thanks. Just kind of following on these points. I mean, in principle, this is a pretty complicated fluid structure interaction problem.
Yeah.
But is the kind of idea that the flow that you generate in the channel, it's really slow, I guess, so it doesn't actually deform the surrounding hydrogel? Is that the idea? Have you thought about like this kind of fluid structure coupling that could potentially happen?
Yeah. I mean, you definitely could do some fluid structure coupling, but I think that's going to quickly get like awful.
Yeah, no, for sure, right? But I
Yeah.
was just wondering if it is important, like especially in the
Yeah.
second example where you had a flow, like Poisson flow, and were the walls in that case a hydrogel as well, or
Yeah. Yeah. Well, so it depends. In like the branching channels, my thinking is that it's all hydrogel. But I guess in the particle trap, you could just have the trap part be
oh,
the
right.
hydrogel.
I see. Yeah, so you could have like rigid walls out in other places, and then
Yeah.
yeah. But yeah, still in any case, like, do you think the flow's ever strong enough to really cause like a deformation or even an internal flow within the gel?
I think it's a good point because you do get your strongest flows at the surface of the droplet.
Mhm.
So that yeah. Yeah, I don't know how fast they are as compared to how fast something has to be to affect the
Hydrogel.
surface of the hydrogel.
Mhm.
Yeah.
Yeah. Well, yeah. Hopefully hopefully you don't have to deal with that ever, but it could make for a cool problem.
Yeah.
Cool. Thanks, Danny.
Thanks.
I think Matt Butler had a hand up
Yeah.
at one point.
So I think my question was one partly answered and the rest of it was not great, so never mind.
Is that all of the questions? I think perhaps speak now or forever hold your peace. Thank you so much, Danny, for being willing to be the first victim here and to kick these seminars off. It's always a tough ask as well when they're a completely new thing. If you all keep an eye on your emails, I'll be in touch shortly with details for the next one. In the meantime, if you consider yourself part of the UK Hydrogels community, stick your name on the directory on the website so that we know who each other are. But thank you so much, everyone, for coming along. It's been really great to see such a good turnout, and I will see you all again next month.